Our warm-up problem for today to get our brains going. Last time, for people that weren't here, we started looking at solids of revolution, which is a solid that is created by taking a region and revolving that region about an axis. And so what I want you to do is take the region bounded by y equals 0, y equals sine of x, from 0 to pi on the x-axis, and rotate it about the x-axis and say, what kind of shape do I get when I take that region? And I'll tell you another thing too. On your exam, I will give you all the pictures from Desmos. But in class, if it helps you, pull out your phone and put Desmos or a graphing calculator with Desmos or a laptop with Desmos, whatever helps you visualize these shapes, okay? So feel free to pull something up and look at it, okay? I will give them to you on your test. I will give you the picture on your test, all right? But you need to be able to work with it once I give you the picture and then visualize what's happening, okay? So you're gonna catch up a little bit, but see, can you picture sine? It's like a wave, right?
Now, when you rotate it over the x-axis, would it rotate?
It comes in 3 dimensions. It flips it. It flips it, exactly. When I say rotation, I mean 360 degrees around the x-axis. So it's going to come out towards you and then wrap all the way around.
Okay.
Like all the way around. So it's going to give you like this kind of shape that comes all the way around, and I'll draw it. You guys picture, what does it look like? Can you think of
it's
what?
Like a spiral, like a screw.
Is it like, oh, I just want you to go from 0 to pi.
Oh.
And you know how you can change it? You know you can always change your settings. Did you guys know you can change your settings on Desmos?
So it'd just be this. So it'd be like a weird.
Like a weird. What do you think it's called? Like I don't know, like a lemon, maybe? Is it kind of like a lemon, or like an egg, or something like that?
Yeah.
Like a lemon or an egg, some shape like that. Oh, I should be recording. But let's do this again. So each cross section perpendicular is a disk. It's a perfect circle. The thickness of each of those is dx because we're cutting along the x-axis. And so I'm adding up or summing all of these disks, and the area or volume for each disk is going to be its cross-sectional area, pi r squared, times its thickness, dx. So that's what we're doing for our setup. We're adding them up from 0 to pi. Every single circle is adding up. Now, the radius is changing. The radius is always denoted, and on your test next week, you will be required on your quiz to show me what is that radius. What is the radius for each of those cross sections perpendicular that you're talking about? The radius always gets measured from your axis of rotation. Okay, always starts at your axis of rotation and goes to the outer curve that's defining your rotation. So this is my radius. It's this distance right here. They should match, right? And your circle's going around, and this is my distance that I'm talking about. And so then you can very easily see the radius is defined by that curve. And so the R value is just that curve, which is sine of x. And so what did you put in here? So what did you do here? Alex, what did you do? What did you put in here? You put
pi sine of x squared.
Sine of x squared, perfect. And sometimes our brain sees sine of x squared as, sometimes our brain sees it like this. Sine to the power 2 of x. So either one, those are exactly the same. Sometimes our brain sees it that way. And then, Ella, did you integrate this?
No, I didn't.
Not yet? Yep, nope, no worries, not far. That's far. Brandon, I thought I heard you tell Jake, or Jake told you. Either way.
We got as a final answer pi squared over 2.
Ah, okay, so now how did you get there? What did you do? What was the next step?
We took out the pi, and then we did
Good.
the power reducing rule.
Ah, okay, slow me down. Hang on one sec. I got to catch up to you. First, you took out pi, and then you looked at it and said this is an even power of sine, and so we need the power reducing formula that we learned last time for integration techniques. So we're going to do power reducing, And let's remind ourselves what that power reducing formula was. It's what? It was
I think it's 1/2.
1/2? Uh-huh. 1 minus the
The
cosine of 2x.
Yeah.
Perfect. Beautiful, 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 beautiful. And so then we're going to integrate pi.
We didn't
So I'll pull that 2 out. And I go 0 to pi. And let's see. So we have 1 minus the cosine. You'll still get the same answer, I bet, if you because sine of pi and 2 pi and 0. Maybe. We'll see. Did you get the same thing, Ava, when you worked through this on this? Let's see. So, all right. Antiderivative of 1, x, thank you, and then x, and then minus, and then Aiden, yeah.
Is it sine of 2x over 2?
Sine of 2x over 2, or 1/2 sine of 2x. Beautiful. And then we're going from 0 to pi. And so then we have to plug in top limit minus bottom limit. So we get that the volume is pi over 2. Erase this little mark here. Beautiful. Pi over 2 times pi minus 1/2 sine of 2 pi minus 0 plus 1/2 sine of 0. So let's see. Sine of 2 pi is 0, isn't it? I think that's 0. And sine of 0 is also 0. Are you guys getting what Brandon said? Pi times pi over 2, which is just pi squared over 2 cubic units. All right, who's got a question? Let's do, nope, that doesn't give me solid. Oh, this will give me solid. Actually, we'll do one more about the x-axis. Let me change this, though. I have to make this x equals 2. Let's do it this way. X equals 2. So let's take y equals x cubed, x equals 2, x equals 0, y equals 0. We'll do y equals 0. So let's do these curves right here about the x-axis. We'll just do one more to make sure we got this down, and then we'll do y-axis. Okay? We'll do one more really fast because it's been a long weekend, and there were quite a few people that were out because of sickness or whatever. So now, this time we're going about the x-axis. I want the solid of revolution generated by taking y equals x cubed, x equals 2 and y equals 0, that region, and rotating it about the x-axis. Did we do this last time? I don't think so. Okay, good. So very first thing is you want to picture what is that region that you're looking for. We are looking for y equal x cubed, x equals 2, y equals 0, and we want to go about the x-axis. So we'll do this example, and then we'll do one about the y-axis. So let's see. Y equals x cubed, 2. 1, 2, 3, 4, 5, 6, 7, 8. 2 cubed is 8. 1 cubed is 1. I got this x cubed shape. It kind of goes like this, but I'm only concerned on this side because... x cubed, I have x equals 2, and I have this one here, which is y equals 0, and I'm looking for the space in between, which is that space, and we're going to send it around the x-axis again, sending it around the x-axis again. Oh, I might have had us draw this picture, but I might not have found the volume. I can't remember what we did last time, but that's okay.
We did something like this, but we were looking at it flipping around.
Ah, good. And when you're cutting, again, for right now, for today, we are cutting perpendicular to our axis of rotation. We'll cut the other way next time. but this time we're cutting perpendicular to our axis of rotation. So when we cut perpendicular to our axis of rotation, again, we're cutting perpendicular to the x-axis, and so you want to be able to say, this is my radius. My radius always measures from your axis of rotation to your curve. So make sure that you can say, my radius is perpendicular to my axis of rotation and goes to the curve. That's hard to see, but that's my radius. And are you guys getting x cubed? Is your radius there? I'm going to wander and make sure we're all good. Pi r squared dx, because we're cutting thicknesses, our limits of integration have to match the variable. And for us, what's your limit? It's going to be 0 to 2. So the limits of integration always match your variable. I will put a little note here. These always match your variable for integration. And if you're cutting perpendicular, you're getting a disk. And let's see. So limit 0 to 2, pi. What did we say was our r? Aiden, did you put x cubed in here?
Yeah.
X cubed. Squared. What do we do to those exponents, guys?
Yeah.
We multiply or add?
Multiply.
Let's check. Let's make sure. Let's see. X cubed squared means x cubed times x cubed. And each x cubed is 3 x's that are multiplied together and 3 x's that are multiplied together. And if I want to put them all, I'm going to count them by adding them up, adding those up. And so what do we do to get our rule? Our rule is x cubed squared is going to be multiply them. So everybody, we should be getting x to the 6th. We forget these rules. I'm telling you, because when we're kids, we memorize these rules and then never use them, okay? So go back to what the concept is. X cubed squared means 2x cubes, and each of those are themselves 3 x's multiplied together, which gives us a total of 6. And so that must mean that to get these, I have to multiply those exponents. I always like to go back to the basics if I ever forget, or if I ever just take things for granted, especially when fractions and things like that. But here we go. I did notice, I wanted to point that out because I think some of us haven't used exponents or roots for a long time, and people were getting the 5th root mixed up on the test. And so I can't remember if it was this class or the other class, but like if somebody gets a 5th root of x, 5 is the root, and so it looks like this. And so a lot of people were writing that differently, and so I just want to make sure we all understand a little bit of exponents. But that being said, Peyton, did you do this antiderivative?
You take out the pi or no?
Take out the pi. Absolutely, I would. 1,000%. And then what did you do?
Then the x to the 7th over
Beautiful. So then you did x to the 7th over 7. And then you plugged in 0 and 2. Oh, good gravy. So let's see. 2 to the 5th is 32. 2 to the 6th is 64. Is it 128 pi over 7? Any questions on that second warm-up with the disk method? It's called the disk method, and I'll put that down here. It's called the disk method because what happens is when you cut perpendicular to an axis of rotation on a solid of revolution, it's always a disk that you're getting when you cut it. Questions? Questions? So I'm going to give you one that you have to think your brain through, okay? I'm going to give you one that's a think through with your brain. Not that one. Hang on, we'll come up here. Ready? So think through on your brain. Same thing. So find the volume of the solid of revolution. Find the volume of the solid of revolution. Created by revolving the region bounded by y equal 9 minus 2x, y equal x, and x equals 0 about the y-axis. And I want you again to make cuts perpendicular to the axis of rotation. So our next warm-up problem is find the volume of the solid created by revolving the region bounded by y equal 9 minus 2x, y equal x, and x equals 0 about the y-axis. Make your cuts perpendicular to your axis of rotation. So let me label all my curves. This one is y equals 9 minus 2x. And this green one is y equal x. And as you guys are telling me, when you rotate this shape, you get this like top. But just like you said, you can't, when you cut it perpendicular to your axis of rotation, you're actually getting two different shapes you have to worry about. You're getting a shape up here, and then you're getting your circles down here. And so you are going to want to split it up into the top curve and the bottom curve, or the bottom cone, if you like, and your top cone. And we'll add those volumes up. So on the top, to get my circles, I have a radius, and that radius on top sits this way, and that's my upper radius. And on the bottom, I have my lower radius, and that's this distance right here. And let's see, volume equals pi, and I'm going to go from here to here, which looks like 3 is my cut point. 0 to 3, and my bottom radius squared is my blue radius squared. And integrating with respect to y. Everybody's doing integrating with respect to y, right? Yes. Then we're going to go 3 to 9. And then this one is my pink radius squared. And you guys know that you can't put a function x in if you're integrating for y. You have to solve for x, right? So actually 2x equals 9 minus y, or x is 9 minus y over 2. And x equals y. Oh, I did that wrong. Sorry, did that wrong. Sat there, did it, and didn't plug it in. 9 minus y over 2 squared. Y squared.
Okay. I got pi over 6.
Is that what you guys did?
I think it's flipped.
Did I flip it? Hang on. Oh, yeah, I flipped it. Thank you, sir. Thank you. My
Oh.
pink is up top. Oh, my God, because I have my wrong colors. Tina is just messing up her colors. Hang on. Let me get my colors back to thing. Let me erase. Thank you, thank you, thank you. I have it all backwards. Thank you, thank you, thank you. Did it all backwards. Let me color coordinate those colors better. On top is my blue radius. I'm going to make him my blue radius because he's up top. He's my blue radius. He's already blue. The other guy's going to be my green radius because he's on the bottom. To find my green curve. He's by my green curve. So my bottom is R, my top is blue, just if I'm color coding. So let me erase this. Thank you, thank you, thank you. Thank you, thank you. My bottom curve became Y. My top curve is 9 minus Y over 2. And you guys are integrating. For the second one, I'm very tempted before I integrate on the second one. I would be really tempted to take this 2 squared out myself. I would probably look at it like this. And then FOIL it out. 9 minus y squared is 9 minus y times 9 minus y, which is just 81 minus, what is that, 38? Nope, 36. It's been a long day. 18. Oh my God, Tina. It has absolutely been a long day. See if we're doing that right. 81 minus 18y plus y squared. I was grading tests till 2 o'clock in the morning, so I think. You could do a U sub if you wanted to. You could, absolutely, if you didn't want to multiply it out. 1,000%. Because it's just linear. Yep, that works perfect. I'm getting 27 over 3 pi for the first part, if I did that right, which is 9 pi. So I think I get the first part. Is that right? Are you guys, am I messing up? I could be, but let's see. The second part is a little more tricky. I'm getting 81y minus 9y squared plus 1/3 y cubed. Ew, it's big. It's big. It's not very fun. Maybe we don't have to get this whole answer. We can just say, I know what to do from here. What's that, 729 minus, oh my God, 9 cubed? Oh, it's the same thing. It's the same thing. Yeah? I think so, because 81 is 9 squared, and if you multiply it times 9, that's 9 cubed. It's the same thing. Plus, 729 over 3 minus 3 times 81. What'd you get? 243 plus, this is where you want your calculator, right? 81 minus 27 over 3. Pi over 4. They go away. Yuck.
I did not take out a negative. You took out a negative.
243 minus 81. What's that? Negative 162? Negative 162.
No, this is right.
Thank you. 2729 minus 27. 702. You guys working on homework? Getting good numbers?
I got good numbers.
Oh, good. I don't know what I got. 6, 18, 486. Oh, man. Okay, so first of all, I got to give you a note. I have to grade all of your tests, right? I am not going to give you something like this and have you work it all the way through on your test. This would be so long and so right? Like, we have calculators for reasons, okay? I have you practice working out integration techniques. I know that we could just plug this into Desmos and it'll integrate it for us. It'll give us a value, just like that, okay? So this becomes minus. It's important, though, to understand, because we're the STEM people, right? Especially if we're teaching STEM, or if we are looking to understand why steps are to get to certain levels to see the patterns. But at this point, heck, I would just plug it into a computer if you want. Or if you want to practice math, you practice math. I don't know if I'm doing this right. So let me see what we got here. What are we getting? We're getting 6, 1, 2, 216 over 3. I know that's divisible by 3 because if I add the digits 2, 1, and 6, I get a number. I think that's 72. 72 is also divisible by 4. Am I doing this all wrong, or are you guys getting something like me? So let's see. So I'm getting 72 pi over 4. I know 4 goes into here. 2, 1, 18 pi. I'm getting 27 pi cubic units. That is not as important, not even nearly close as important and I should have just stopped here instead of being so OCD about it. I want to make sure, can everybody get to the volume setup right here? This is what's important to me, because then we can always go to Desmos. We can always go and evaluate it out if we need, okay? But I need to make sure you guys can get to here. Can you guys get to here, okay? And do you know how to check your work on Desmos? Have you guys ever done integration on Desmos? So on Desmos, if you want to do, let's just say an integral from 0 to 3 pi y squared, you would just type int. Here, let me show you. That is that. Now, I want to take this same region, and instead of rotating it about the y-axis, rotate it about the x-axis. Same region, but instead of going about the y-axis, rotate it about the x-axis. So let me get a fresh screen, and let's do the same thing, but this time I want to rotate this sucker. So I want to rotate this shape, so add my saved picture, which is this one, and I want to take the same shape, bounded by the same curves, okay? And this curve was y equal 9 minus 2x. And this curve was y equal x. And this line here is x equals 0. And I want this region in there. And this time I want to send it about the x-axis. So find the solid of revolution. Find the volume of the solid of revolution. Created by revolving the same region which is bounded by y equal 9 minus 2x, y equal x, and x equals 0 about the x-axis. And so what do you notice that's different? Okay, so you're going about the x-axis. You notice that it's going to be a funky shape, isn't it? It's not going to be the same picture. What does it look like? Can you guys picture it? What's it looking like to you? What are you thinking?
It should be washed.
So this goes around, right? We got this shape, and it's coming around, and it's got this. So can you picture kind of like a volcano? I think of a volcano. I kind of see a volcano out of it. I do. I kind of see a volcano. Little bit of a volcano around there, kind of like. And of course, I mean, you can't see this. You can't see this, but it's so there's a lot of dotted things going on here that's underneath the surface of this. But you guys kind of see a volcano there sitting on its side. So what makes this shape a little different than this shape here is that this sucker was solid, like wood, like a solid wooden top. Whereas this volcano actually has a space in the middle of it for lava or whatever, air or whatever. And so it has inside of it a hole. Everybody see that we've got a hole in there. So now, when I cut it, remember, right now we're all about cutting perpendicular to the axis of rotation. So if I make a slice, so if I cut it perpendicular to my axis of rotation and take a slice, what does that cross-section look like? What does it look like if I slice right in the middle of that volcano? And sometimes it's hard for people, but they cut the top off and then look down at what you see. You know what I mean? Like, cut the top off, and what do you see? What do you see? It's like a washer. Do you guys see that what happens is you see a circle, a disc, but it's got a hole in the middle of it. So when you cut perpendicular to your axis of rotation, undo. When I cut perpendicular to my axis of rotation this time, right? I get this what we call a washer. So it's a perfect circle inside a perfect circle. So we get what's called a washer when we pull it out. So we get a washer. And so the idea is these washers, well, the washer is actually comprised of, if I want to get the area for a washer, what could you do? If you wanted the area, yeah, Aiden.
Do the area, the outside circle minus the area of the inside.
Is that what you were thinking? Take the big circle. So that's how I think of a washer. If I'm looking to get the area for that washer, if I'm trying to get the area of the top, right? The top of that, the area of the top of that washer right there. Because it has a thickness, and we know because we're cutting perpendicular to the x-axis, the thickness of that washer runs along the x-axis. So it's a dx thickness. But the area on the top is, in fact, a big circle minus a little circle. So we have a big circle, and then we're taking out or subtracting from it a little circle. And so if I visualize it, I have this big radius here, this big R here. And so the area of this one is pi r, big R squared. And then I have another circle, a little one in here. And that has a little radius, and the area of that guy is little r squared. And so if I want to get the area of one slice of a washer, it's going to be pi times the big radius squared minus pi times the little radius squared. And so let me draw my picture in. So if I'm cutting perpendicular to the x-axis, my radiuses are always cut perpendicular to your axis of rotation. So the big radius is the radius that goes all the way to the outer curve. That would be called my big radius. And again, on your test, I will have you put these in to say, okay, we're using the washer method. We're rotating this about this axis. Draw for me big R and little r. So big R and little r always go perpendicular to your axis of rotation. The radiuses are cut perpendicular to the axis of rotation. And when you do that, you can kind of see the distance. That big distance is defined by this outer curve. The little distance is defined by the inner curve. So it's the little distance and then it's the big distance with the hole in between, right? So the little distance and then the big distance. So when we go to set up our volume, let's see. Oops. Anybody want to take a gander or want to help me out here? What are you going to do to set up your volume? It's going to be an integral. So again, we're cutting perpendicular to the x this time. Ooh, why do I have pi? Because I didn't change my Desmos. Darn it. I didn't change my Desmos. Darn it. Well, it's okay. What are my limits? You guys going to 0 to 3 along the x-axis? And we're integrating with respect to x because we're cutting along the x-axis. Pi, big radius minus pi, little radius. All righty. Erase. You guys want to pull the pi out? Is that okay if I pull the pi out? I'm going to pull my pi out, put him out front. And that's going to give me big radius, 9 minus 2x squared, which is big radius squared, minus little radius squared. So that's going to be x squared. And now I'm back to x's, right, because I'm integrating with respect to x. I don't want to work this all out just because I don't want to work it all out, although we could. I will tell you one thing. It will be different than the answer you got before. And that's because the shape that you get by rotating around an x-axis versus a y-axis is different, right? One shape we got like this top kind of shape, and this time we're getting like a volcano. So the volume is very different because they're just different. The way you're rotating causes different shapes to erupt, different dimensions, different distances. I am going to do 81x minus, if I'm doing this out, 18x squared plus, oh, this guy is 3x squared. What's that? X cubed. Integrating from 0 to 3. So give me 243 minus, shoot. I said I wasn't going to do this. 18 times 9, 7, 2. I can't do this in my head. 162, I think, plus 27, I think. Well, it's a big number, if I did that right. 18 times 9 is 72. I think that's 162. Yeah, because it's 18 times 10, 180 minus 18, 162. Yep. And that gives me, 81 plus 27. Oh, I don't think this was the answer I got last time.
Plug it into my calculator.
Are you getting 108 pi? 108 pi? Cubic units? Is that what you got, Ava? Cubic units? Oh, I don't think I got that in the last class. I think I added wrong. We might have. Maybe we got it. I can't remember. Questions? And we can always check it on Desmos. Like if online in Canvas, you can see some pretty pictures again. So you can go in, you can draw the picture, you can practice drawing your big radius and your little radius, you know what I mean? Make it all pretty for your notes to make sense of what's happening with everything, okay? So that's all online in Canvas for you if you want. Also, I have a problem for us to finish as our last end of the day exit curve come out of the room. Just to practice washer method, we'll do this last one. When we come in, we'll do washer method to start, okay? Disk method maybe, and then we have a whole new method. So I am going to strongly encourage you, once you get your cross-section homework due, that's tonight, if you can tomorrow, before you get into class on Wednesday, try to get as much done on that disk and washer method as possible. Because I have to introduce another method, cylindrical shells, and if you haven't already practiced disk and washer, you're going to be crazy. It's going to be too much at one time. And does that make sense? Because then we're going to cut not perpendicular to our axis of rotation, but parallel to our axis of rotation. And so we get entirely different shapes that erupt when we look at that kind of integration. So just from practice. So here's your practice problem, and we'll practice a couple more next time. Oh, hopefully we get to cylindrical shells. I forgot. We have to go around different axes. We'll see. So a solid of revolution is formed by revolving this region bounded by the following curves. Y equals x cubed, y equals 8, x equals 0, about the x-axis. What makes this solid different? It's got a hole in it, because we just answered that question by doing the problem before it. It's a hole in this solid, but I want you to use this as a practice right now before you exit to say, okay, I think I understand washer method. I think I understand what I'm supposed to do here when I have holes in my graphs. 1, 2, 3, 4, 5, 6, 7, 8. In my solids of revolution. Y equals x cubed, we said was a nice parabola, kind of. Well, not quite a parabola. Actually, it's not. It's the cubic function. And x equals 2. Nope. Y equals 8. Undo. Y equals 8 does this. It's a horizontal line. X equals 0. So we're looking at this shape rotated about the x-axis. Can you guys kind of see? You're getting a... It's kind of like a volcano, but I think this guy, not quite. I think this one looks more like a shape we drew last time. Like that shape that you put a coin that goes down the coin, like a whirlpool, kind of. inside of a cylinder, like this whirlpool inside a cylinder. And so we want this volume, and I want you to get the volume cutting perpendicular to the axis of rotation. So we're going to cut perpendicular to our axis of rotation. And the idea is you should be having a hole. So it has a hole. So you're going to want to see it has a hole. What do I do with my hole? How do I set my formula up? I'm cutting perpendicular to my axis of rotation. So getting washers. I should be getting washers, right? I should have a hole. And I should have an outer radius and an inner radius, because our radiuses always are perpendicular to our axis of rotation. God, you guys are such good drawers. I'm telling you, you guys have it down. It took me a long time to draw these three-dimensional shapes. You guys are really good at it. You can draw these.
Mine are in a state dimension.
Can you see it?
Yeah.
You can see
I
it.
just can't draw them.
And can you and for your test, could you put the R values in, the big R and the
Yeah,
little R?
I did that.
Good,
I just
good,
can't
good.
draw.
Oh, I did not
Good,
see that.
good.
Color.
It just takes lots of practice. It just takes lots of practice.
Choose the size.
How are you? Got it? Good? Yeah. Oh, nice. You did it. Ah, be careful. Be careful. You're doing everybody does. And so I'm glad you did it. Take your big radius, square.
So just do 128
Big circle,
over seven.
square.
128
Are you with me?
Huh?
Do you see?
And you just multiply
And
by
then
128.
little circle, square. I know, you do what everybody does. And then you get the wrong answer at the end and you can't figure out how you got the wrong answer at the end. Do you see it? Thank God, mistakes allow thinking to happen. Very good. Very good. It won't tell you though, will it? It won't tell you. Because you would have had it set up the same way. Like you would have got the right answer. Then you'd go into the web work and you'd be like, oh my God, I'm back in my brain again. So I'm glad you did that because it's called mistakes allow thinking to happen. Once you do it, then you remember it. I've done it before. I still do it though. I mean, mistakes are supposed to allow you to think to happen. Yes, separate. Beautiful, beautiful, beautiful. Do you go separate? Yeah? Everybody's going separate on this? Perfect, perfect, perfect. Arden, question. I really should put my limits on. Did you go 0 to 2? Question. Ava, question. Oh, because I'm being crazy again. We're going to get rid of that. Is that what you're going to say? Thank you. Because I want a double pi. Because I'm being crazy. Let me pull that pi back out. And let me just make it with my big radius squared minus my little radius squared. And so that should be your setup. That should be your setup. Your big radius is the outer curve, which is y equals 8. Your little radius is that inner curve there, which is y equal x cubed. And then when you put it all together, you're going to have pi. And then that's going to give you, what, 64x minus 1/7 x to the 7th. What's really cool is 2 times 64 is 128. So that's 128 minus, and 2 to the 7th is also 128. So really what I'm doing is I'm taking, what's that, 6/7? So it's really going to be 6 pi times 128 over 7. I don't think 7 goes into it. Did you get a big number on top there?
I just stopped at the
Yeah.
2 to the power 7.
Gotcha.
It was like 768.
6, 7,
768.
768 pi over 7 cubic units. Cubic units. Okay, but just checking. How are you guys again? It's the setup that I'm worried about. It's the setup that I want.